Hello, welcome to Parent Functions Part 1. This is the first lesson in Unit 2, Manipulating Graphs. Here are the 9 different types of parent functions. We're going to go through each one as quickly as possible. Get a little more in depth on each of these. The first is a linear function. Okay, a linear function is, of course, just a line. All right, and we're going to go ahead and graph these. I'm going to really quick put the points up on the chart with their y's so that you can see them really fast. Just to let you know, I'm going to do all the x's that you see listed here for sure on each of our graphs. And then, maybe also a couple more to help us see the function a little bit better. Okay, if you plug in all those x's, you are going to get out the y's that you see. F of x equals x. If you plug in -2, you get out -2. Plug in -1, you get out -1, and so on. All right, I'm going to go ahead and graph those. There are those 5 points graphed, and then, of course, we can put our line through that. All right, now let's fill out the table below. Is this a function? Vertical line test? Yes, it is. All right, what's the domain? Domain is all reals. That's all real numbers. That's the same thing as saying -infinity to +infinity. How about the range? The range is also all real numbers. Okay, so all the possible y's will be all the real numbers. The x integers crosses the x-axis at 0, 0. And then the y-intercept, I should have said x-intercept earlier. Okay, the y-intercept also at 0, 0 crosses the y-axis. Then don't worry about that last box. First function, linear functions. Second function, quadratics. Then I'm going to go ahead and plug in those x's and get out the following y's. Okay, if I plug in -2, I get out +4. If I plug in -1 in square, I get out 1. Plug in 0 in square, I get 0, and so on. If I graph those, it looks like so. And of course, I can give those a shape, which you probably already know is a parabola. All right, is this going to function? Vertical line test, yes. The domain looks like x is all reals. The range, x has to be, or excuse me, y has to be greater than or equal to 0. Okay, this only goes down and touches 0. X-intercepts, where does this touch the x-axis? Oh, at the point 0, 0, right at the origin. Where does it touch the y-axis? Again, right at the origin. That is quadratic things. We have squares, x squared. The next, f of x equals x cubed. Well, this is a cubic function. And then we're going to plug in our 5 numbers for f of x equals x cubed. And then we get out the following y's. -2 cubed would be -8. -1 cubed would be -1. Plug in 0, we get out 0. Plug in 1 cubed, we get out 1. And 2, get out 8. All right, then I'll graph these. As you can see, our 2 and -2 points went off the graph. The graph only goes to 7, not 8. Okay, and then if I give this a curve, it looks something like that. Okay, where it kind of levels out or gets a little less steep near the origin, and then continues back up to infinity. Okay, is this a function? Yep, passes the vertical line test. What's the domain? All possible real numbers. There's not an x that we can't put into this. What's the range, all possible y's. Okay, there's not a y this won't reach. Okay, where does this cross the x-axis? Crosses at the point 0, 0 again. Where does it cross the y-axis? Okay, it crosses the y-axis again at the point 0, 0. And then that's the cubic function. Moving on to the fourth function. This one's a little interesting. F of x equals the square root of x. We're just going to call this a square root function. All right, and then I'll plug in the usual x's and get out something interesting for this one. Now, if we look, -2 and -1, okay, I'd have dashes. That's because it's impossible to square root a negative number. Okay, so our graph won't have any values to the left of the x-axis, or excuse me, left of the y-axis. If I plug in 0, square root of 0 is 0. If I plug in 1, square root of 1 is 1. If I plug in 2, okay, I don't get a whole number or an integer out of there. Okay, so I have to kind of approximate it to 1.4. It might be better for graphing if we actually plug in another number, one that is squareable, if you will, square rootable. And that number you might be thinking already is 4. Okay, if I plug in 4 and I square root it, I'm going to get out 2. Okay, now I put those 3 points on the graph for us. I didn't count 2. I didn't put that on there, but put 1, 2, or 0, 1, and 4. And I give that the curve that's starting to form. It's going to look like that. You can plug in a couple more points if you want to be more sure. So you ask yourself, is this a function? Okay. Yes, based on the sketch, this is a function. What is the domain? X has to be greater than 0 here. Okay, we can't go into the negative numbers, but we can include 0. Should say greater than or equal to 0. The range, based on this graph, y also has to be greater than or equal to 0. Okay, where does this graph touch the x-axis? 0, 0. Again, where does it touch the y-axis? 0, 0, just like the other ones. Okay, and that's the square root function. Fx equals the square root of x. Next, we have fx equals the absolute value of x. That's what those 2 bars mean. Okay, this is just called an absolute value function. If you don't know already, absolute values just indicate how far a number is away from 0. So I plug in -2. -2 would be 2 units away from 0. Plug in -1. That's 1 unit away from 0. 0 is 0 units away. 1 is 1 unit away. And 2 is 2 units away. Or it just makes them positive. Another way to think about it. Okay, I'll plot those points. And there you can see the v that's starting to form. Well, that is what an absolute value function looks like. There will be a v. So every time you have absolute value bars, you can pretty much expect there to be a v on your graph. Is this a function? Yep, passes vertical line test. Domain. Okay, this looks like all reals. There's no x's that can't go in there. The range, everything up and down, everything's bigger than 0. So everything here is y is greater than or equal to 0. Where does it hit the x-axis? 0, 0 again. Where does it hit the y-axis? 0, 0. And that is our 5th parent function, absolute values. All right, next, f of x equals 1 over x. These have an interesting name. They're called inverse functions. Then I'll go ahead and plug in our usual x's and get out the following y's. And I get the points on the graph that look like that. And that's kind of hard to know what's going on. So I'm going to go ahead and plug in one more point. I'm going to plug in a -1/2 and +1/2 into both of these as well. If I do that, 1 divided by 1/2 is 2. 1 divided by -1/2 is -2. So I get the following points: 1/2, 2, -1/2, -2. now you can kind of see what's going on. If I were to continue to plug in points, I would get curves that looked like this. So in the first and third quadrants, kind of they approach the x and y axes, but never actually touch them. Is this a function? Yes. That's the vertical line test. What's the domain? Okay, well, there's one number that this can't be. Okay, so you could write it like all reals except x doesn't equal 0. Can't equal 0. Same for the range. All reals except y can't be 0. Remember, these curves don't touch either axis, so it can't be 0. X can't be 0, y can't be 0. Where does it cross the x-axis? It doesn't, so there's no x-intercepts. Where does it cross the y-axis? It doesn't, so there's no y-intercepts. That is an inverse function, or inverse rational function you might see sometimes. This one is a little interesting. F of x equals a, which a is just a number, to the raised to the x power, where a is greater than 1. This is exponential growth. For the purposes of this graph, I'm just going to plug in 2 as our a, so a equals 2, and use that as our function. F of x equals 2 to the x. And I'm going to plug in those x's. Okay. And I get out the following y's. Negative 2, 2 to the negative 2 is negative 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to 2 is 4. And if I plug those, or put those points on my graph, and you get those points and a graph that looks like this. It's exponentially growing, okay, getting bigger, bigger, and faster, farther and farther away from 0 faster. All right, so it looks something like that. Right, is this a function? Yes, passes the vertical line test. What's the domain? Domain looks like all real numbers. There's not an x that can't go into that. The range is a little more interesting. It looks like y has to be greater than 0, and of course it never touches 0. Okay. What are the zeros? Well, this never touches the x-axis. Okay, so there are none. No x-intercepts. This does touch the y-axis. This is where this is interesting. It touches the y-axis at the point 0, 1. And that's true for all of our exponential growth. So it doesn't matter, okay, what we put in there. It'll touch at 0, 1. Doesn't matter what we put in there for a, it'll touch at 0, 1. And that is exponential growth. All right, 8 looks very similar to 7. F of x equals a to the x, where a is less than 1. This is going to be exponential decay. And this should really be written as a has to be between 0 and 1 to be more accurate with exponential decay. I'm going to use the following f of x equals 1/2 to the x to show that, and put in our usual x values to get out the following y's. And you might notice that this is just the reverse of what we had for an exponential growth, which makes sense. It's exponential decay, so it's going to be the opposite. So if we plot those points, we get a graph that looks something like this. We're slowly from left to right decaying, or getting less and less and less, getting closer and closer to the x-axis, but not touching it. Okay, is this a function? Yes. Passes the vertical line test. What's the domain? All possible x's, all reals. What's the range? Again, okay, y has to be greater than 0. We never actually touch the y-axis. It's just above it, or the x-axis, just above it. Does this cross the x-axis? No, so there's no zeros. Again, just like exponential growth. Where does it cross the y-axis? Where's the y-intercept? Again, at 0, 1. And that's true for any exponential decay, because when we raise a, whatever a is, in this case a is 1/2, when we raise a to the 0 power, it'll always be 1. That's exponential decay when f of x equals a to the x and a is less than 1. And the last one, f of x equals log of x. Okay, it's a logarithm function. I'll plug in the following x's and get out the y's. You see that -2, -1, and 0, if you plug them into a logarithm, don't actually yield anything. Not until 1 do we get a number, and that's the spot 1, 0. 2 is kind of a weird decimal. 3 is kind of a weird decimal. In fact, based on logarithms and the way they work, not until 10 do we get another integer, and that yields only 1. So if we graph those values, it looks something like this. Yeah, okay, and it's kind of hard to see what's happening, but if we were to graph even more points between 0 and 1, we would give a curve that just starts to bend, continue like so, on forever. Now it gets closer and closer and closer to the y-axis, but doesn't actually touch it. And on the other side, as it approaches infinity, it goes up and up and up, even though it's a very, very shallow curve. Is it a function? Yep. Okay, no x's share has multiple y's. What's the domain? X here has to be bigger than 0. Okay, it can't cross, we don't ever cross the y-axis. The range can be all reals. Even though it looks like it levels off up and down, it doesn't. This will continue grow. That's just true of logarithms in general, forever. So all the possible y's. The zeros, does it cross the x-axis? Yes, it does. It crosses at the point 0 or 1, 0. Does it cross the y-axis? Nope, we never actually get into negative numbers, so there is no y-intercept. And that is parent functions. Go ahead and check your unit schedule for an assignment, for the assignment for all these parent functions.